Greetings everyone. This is a project prepared by EKT3 Computer Network Engineering students. Our title for this project is Frequency Response of a Robotic Position Control System. My name is Liu Minyi and I will now begin the presentation. This is our introduction. Robotics is an interdisciplinary branch of engineering and science that includes mechanical engineering, electronic engineering, computer science, and others. Robotics also deals with the design, construction, operation, and use of robots, as well as computer systems for their control, sensory feedback, and information processing. These technologies are used to develop machines that can constitute for humans and replicate human action. About the 6 degrees of freedom, it refers to the freedom of movement of a rigid body in three-dimensional space. Specifically, the body is free to change position as forward or backward, up or down, left or right translation in three perpendicular axes, combined with changes in orientation through rotation about three perpendicular axes, often termed yaw, pitch, and roll. Robot arms are described by their degree of freedom. This number typically refers to the number of single-axis rotational joints in the arm, where higher number indicates an increased flexibility in positioning a toes. The aim of this project is to determine the 6 axes or degrees of freedom by calculating the unity feedback position control system for a force sensing joint. We also aim to determine the gain and phase margin of the system to design a compensator with desirable phase margin. We have 3 objectives. First, determine the gain and phase margin of the system. Second, design a compensator with phase margin of at least 35 degrees. Third, demonstrate the result using MATLAB. For the methodology part, initially we need to replace the S domain of the transfer function to j omega. Next, we need to split up the function into its constituent parts and identify constant, poles at origin, zeros at origin, real poles, real zeros, complex conjugate poles, complex conjugate zeros. After that, we can start to plot the Bott diagram and consolidating the Bott diagram. Lastly, we also need to design a compensator and determine which compensator that would produce the phase margin with at least 35 degrees.
Greetings everyone. My name is Lim Kelvin and I'm going to continue our presentation regarding the result part of the project. We are going to design a compensator. A unity feedback position control system for a force sensing joint has an open loop transfer function as shown, with assumption of k equals to 10. Our first step is to replace the s with j omega. The transfer function is as shown. Next, we are going to determine the magnitude plot and the phase plot. The writing of the equation are as shown. This is the graph representation by MATLAB, which clearly shown the magnitude and the phase graph. When we zooming up into the graph, we can clearly see that gain margin of 6.2 dB at frequency of 8.66 radian per second. Phase margin at 24 degree at a frequency of 5.88 radian per second. With the details that we gather, we are now trying to design phase lead compensation network. Now we are calculating the phase margin needed. After the calculation, we getting a result of 26 degrees. Now we are trying to solve for the alpha and tau, and the calculations are as shown. After we get all the value we need, we will now substitute the value into the transfer function GC. We will then gain a new function of GCSGS as shown. After we plot the new line, we get a new value of gain margin and phase margin as shown. The new gain margin is 8.97 dB at a frequency of 12.1 radian per second, and the phase margin is 28 degree at a frequency of 8.22 radian per second. The new phase margin are lower than what we desire, which is at least 35 degree. Thus, we proceed with phase lag.
Greeting everyone, my name is Tan Wei Jian and I'm going to continue our presentation regarding the phase lag compensation network of the project. By using the initial gain margin and the initial phase margin, we are going to determine the new phase margin in order to design phase lag network with addition of 5 degree as a safety margin. From the calculation shown, we get negative 140 degree and we are going to find new frequency at phase of negative 140 degree. From the graph shown at phase of negative 140 degree, the frequency obtained is 4.5 radian per second. To find the new transfer function, we need to determine the value of omega z, alpha, and tau. To proceed with the calculation of omega z, we need to plot 0,1 decade below the new crossover frequency. The steps of doing so is as shown. This is the graph shown after plotting the new line with comparison of the initial line. After we zoom in, we obtain 3.6685 dB of gain from the newly plotted blue color line at frequency of negative 140 degree. After getting the gain, we are going to determine the alpha and the tau value. The detailed steps are as shown. After obtain all the required value, we are going to determine the new transfer function of GCS. Finally, we obtain the new transfer function of GCS-GS. After we plot the new line, we get a new value of gain margin and phase margin as shown. The new gain margin is 9.57 dB at frequency of 8.52 radian per second, and the phase margin is 37.9 degree at frequency of 4.53 radian per second. The phase margin meets our requirement of at least 35 degree. Thus, phase lag compensation network are better than phase lead compensation network.
Greeting everyone, my name is Liu Wei San and I am going to continue our presentation regarding the result of the project, which is also the conclusion part. These are the value comparison of phase lead compensation network and phase lag compensation network. From the comparison, we are required to design a phase lag compensator so that the phase margin will be at least 35 degree. And because the phase margin of the phase lag compensation network having a phase margin of 37.9 degree. Therefore, phase lag compensation network is chosen.